So today we continue with semiconductors, part 5. Now let us see the transistor as an amplifier. This is a typical circuit diagram of the transistor as an amplifier. We have seen all the configuration. Out of that, the C configuration using the NPN transistor is shown here. So that's the base emitter voltage. Input voltage is applied across it. The base current across the resistance, that is along the resistance RB. The I is the current to the emitter. This is the collector emitter voltage, the collector current IC, load resistance RL, and the voltage, output voltage here. So we have the input voltage and the amplified output voltage. Let's see how it works. So we have here again the circuit diagram. When the input voltage Vi is not applied, applying Kirchhoff's law to the input loop, VBB is equal to VBE plus IB into RB. Kirchhoff's law to the output loop, then VCC is equal to VC plus IC into RL. When AC signal is applied, that is, Vi is not 0. Ri is the dynamic input resistance as we had discussed in our earlier slides. VBB plus Vi is equal to VBE plus IBRB plus delta IB into RB plus Ri. The change in VBE can be related to the input resistance and the change in the base current IB. From equation 3, since RB is very small, Vi is equal to delta IB into RB plus Ri, that is equal to delta IB Ri where RB is neglected. Change in the base current IB causes a change in the collector current IC. AC current gain beta AC is almost the same as the DC current gain beta DC for the normal operating voltage. Therefore, beta AC is equal to IC upon IB. That's equation 5. The change in the voltage drop across the load resistance is the same as delta VC because VCC is constant. Delta VCC is equal to delta VC plus delta ICRL, that is equal to 0. Therefore, delta VC is equal to minus delta IC into RL. That's equation 6. The change in the output voltage, delta VC is the output voltage VO. But we know delta IC is equal to beta AC into delta IB. Substituting this in equation 6, VO is equal to delta VC, that is equal to minus delta ICRL, that is equal to minus beta AC delta IB into RL. The voltage gain AB is equal to the output voltage upon the input voltage. That is equal to VO by VI, that is equal to delta VC upon delta IB upon RI. That is equal to minus beta AC delta IB upon delta IB, which gets cancelled, RL upon RI. So from equation 4 and 7, AV is equal to minus beta AC RL upon RI. That's equation 8. The negative sign indicates that the output voltage and the input voltage are out of phase. The power gain AP is equal to VO into IC upon VI into IB. That is, the whole equation we get here IB and IB gets cancelled off and we get it as AV into beta AC. That is the voltage gain into the AC current gain. So the transistor can be used to gain power because beta AC is greater than 1. Now let's see what's analog and what's digital signal. Now this is an example of an analog signal, that's a sinusoidal signal. It's a voltage versus time graph. And if you take a digital signal, then the signal is voltage or current, it can be anything, which has only two discrete values and is called as digital signals. Example, square waves has either low 0 volt or high plus 5 volts. An electronic circuit which handles only a digital signal is called a digital circuit. The branch which deals with digital circuit is called as digital electronics. Now let's see what are logic gates. A digital circuit with one or more input signals but only one output signal is called a logic gate. It is a switching circuit that follows certain logic relationship between the input and the output voltages. The word gate because it controls the flow of signal or information. The output of the logic gate can have only one of the two states, low voltage or high voltage. The output depends on the input. There are 5 common logic gates, not or, and, or, nor, and NAND gates. Their function is defined by truth table. Truth table gives all possible combinations of the input and the corresponding outputs. It defines the function, shows the behavior, and analyzes the logic gate. The mathematical statement which provides the relationship between the input and the output of the logic gate is called as a Boolean expression. This is the NOT gate. That's a truth table. It is a basic logic gate in which if input is low, output is high. And when input is high, output is low. Output is negated version of input, hence it is called an inverter. Now let's see what's an OR gate. So that's the symbol, that's the truth table. It's a basic logic gate again in which there are 2 input and 1 output. It performs the function of addition. When any one input is high, it gives high output. Both inputs are low, then the output is low. As you can see, 0 plus 0 is 0, low plus low is low, high plus low is high, and 0 plus 1 is 1 again. And 1 plus 1 is 1, that is high plus high is high. Now we go to the AND gate. So that's the AND gate, that's the truth table. So it's a basic logic gate in which there are 2 input and 1 output. It forms the function of multiplication. When both inputs is high, it gives a high output. If any one is low, the output is low. Now that's the NOR gate. That's the symbol, the truth table here. So it's just a logic gate in which there are 2 inputs and 1 output. It performs the function opposite of addition. If any one input is high, it gives low output. Both inputs are low, then the output is high. Now that's the NAND gate, the truth table here. Logic gate in which there are 2 input and 1 output. It performs the function opposite of multiplication. When any one input is low, it gives high output. Both are high, then the output is low. Now let's say the exclusive OR or the XOR gate. Now this is the symbol of 2 input XOR gate symbol it is. Now that's the truth table. See the function. It is A plus that B is equal to A bar dot B plus A dot B bar. That's the output Y. An odd number high or 1 gives high. When there are 2 inputs and 1 output, this is the truth table shown here above. The output is high when the inputs are at different logic levels with respect to each other. It compares 2 logic levels and produces an output value which depends upon the input condition. Hence, it is extremely useful in computational logic circuits. So that's all for today. Thank you.